This one is the latest look at X-rays and gamma rays in thunderstorms. And we'll have three speakers who will speak in this order. Joseph Dwyer, Professor of Physics at the Institute for the Study of Earth, Oceans, and Space at the University of New Hampshire in Durham. Pavlo Kochkin, he's a research scientist at the Eindhoven University of Technology in Eindhoven in the Netherlands. And then we'll have Themis Kronis. He's a research associate with the Earth Systems Science Center at the University of Alabama in Huntsville.
Thanks, Peter, and good morning. Okay, here we go. Okay, so my job is to give you a little bit of an overview of the field. So I'm going to be talking about the X-ray and gamma ray emissions from thunderstorms and lightning. This is part of a new field of study called high-energy atmospheric physics. So we know that inside our atmosphere there are several bright sources of X-rays and gamma rays. This is a bit of a surprise. People really didn't know that this was going on until relatively recently. So one source of X-rays is normal lightning. We've seen that lightning, when it approaches the ground, emits very bright bursts of X-rays. These are the kind of X-rays that you might see getting a CT scan, for example. And lightning can somehow do this under normal atmospheric pressure. And these measurements have been done near the ground. We also know that thunderstorms can emit gamma rays, and they can emit it in sort of a glow. So when aircraft fly past thunderstorms or balloons go inside thunderstorms, what they see is that the thunderstorms sometimes continuously emit gamma rays. Now, gamma rays are very high energy X-rays. And so this is really strange that a thunderstorm, a big puffy cloud, would be emitting gamma rays sort of like astrophysical objects, like black holes or supernovas would do. And this emission seems to be continuous. When the aircraft goes by, it will see the gamma rays, and eventually as it goes past, they'll disappear. And if the aircraft comes back, then sometimes we see the gamma rays again. So it seems to be a continuous emission. And the third category of emission I want to tell you about are the terrestrial gamma ray flashes. These are very powerful bursts of gamma rays from thunderstorms, sort of a monster explosion of gamma rays. They're much shorter than the glows. They're very powerful. In fact, they're so powerful that they can be seen from spacecraft in low Earth orbit. And there's a lot of atmosphere between the thunderstorm and the spacecraft, so this is quite amazing that spacecraft hundreds of miles away can see these things. This is a NASA picture of what one of these might look like. This is an artist's impression with the gamma rays in pink. These terrestrial gamma ray flashes, or TGFs, they occur all over the world wherever there are thunderstorms. We know that they're closely associated with thunderstorms, but we really don't understand the details. We know that they're coming from thunderstorms, but exactly how thunderstorms are emitting these and what kind of storms, we really didn't know that much about until just recently. You'll hear some more about that in this press conference. So let me just summarize. So there's many mysteries remain about how thunderstorms and lightning work. And we know that there are bright bursts of X-rays and gamma rays from lightning, and there's glows from thunderstorms, and then the very powerful terrestrial gamma ray flashes. And so why is this important? Well, since we don't understand how thunderstorms and lightning work very well, these are clues. This is a way of probing what's happening inside the thunderstorms and what's going on with lightning. So this should be giving us information about how these phenomena occur. So thank you very much.
Good morning. And we recently performed an experiment that is not easy to repeat, I can assure you. We took an aircraft, a real one, and we equipped it with many different sensors and sent it right into a thunderstorm to measure all these phenomena that were just introduced by Professor Dwyer a minute ago. So Airbus supplied us with the aircraft, with a huge one, and together with Dutch National Aerospace Laboratory, we developed a system called ILDAS that could measure many lightning parameters, not only lightning, but also the thundercloud parameters. So together with all these detectors, there were 2 gamma ray detectors. So we basically could measure the gamma radiation from thundercloud and from lightning itself, right up there in the thundercloud. And this is how it looks from the inside. So this is the internal view of the aircraft. So just to give you an impression that it's not just a normal commercial airplane, but this is specially developed test aircraft to perform these measurements. It's full of sensors and full of data acquisition systems. And here you see 1 day of this campaign. So it was 5 days campaign. So the aircraft flew through thunderstorm during 5 days. And here you see an example of one of it. So the aircraft stays on its base in Toulouse, this is in France, and that time there was a huge thundercloud developed over northern Italy. And so the aircraft takes off, as you see at about 1 o'clock, it goes up and flies towards the thunderstorm. Then it descends down to 4 kilometers altitude and enters the thunderstorm to measure the radiation inside. Imagine how brave should pilots be. I mean, because normally pilots just avoid aircraft, and in this case, they have to go there and measure all this high energy radiation from all this nightmare around. So here you see the altitude profile as a blue line, and you see they're trying to keep certain altitude, like 4 kilometers height, but it's so difficult. So they're just bouncing up and down continuously. So it's huge turbulence inside them. And then they flew there for more than 5 hours. It's more than 5 hours of extreme turbulence, and then they go up again and go back to their base. And here you see the radiation that were measured inside the aircraft during this flight. So you can recognize that in this case, this is other time scale. At about 11 o'clock, the aircraft takes off, and it gains altitude and flies towards the thundercloud. Then it descends back, and you see by arrows I indicated here lightning strikes to the aircraft. So there were more than 20 lightning strikes during these 5 hours inside thundercloud. And yeah, and then here you see this might be an indication of a long gamma ray glow that was just introduced by Professor Dwyer. And so we have measured this phenomena. And also we've measured radiation from lightning, and we can confirm that lightning is indeed very bright in X-rays. And I'm not going into detail about how it works, but just to conclude that high energy radiation from lightning and from thundercloud was measured right in situ, right up in thunderclouds. And we got a lot of highly synchronized and high resolution data. And all what we measured is very well consistent with what have been measured from the ground. So this is basically the first time when the radiation from lightning has been measured at high altitudes, so at lower pressure. So we confirmed that this is it's lightning. The radiation is lightning property and not the altitude effect. And yeah, thank you for your attention.
Ladies and gentlemen, thank you for coming, and let me start by saying that I feel deeply privileged to present a work that was started and embraced by 9 more esteemed experts in the field. And let's talk about the TGF origins, like Professor Dwyer mentioned. TGF are the most energetic phenomena on planet Earth. We now know, thanks to worldwide observations of lightning networks, like the one by the University of Washington, led by Professor Holdsworth, and the Earth Network, Total Lightning Network, led by Stan Chris. We now know that these TGFs relate to the so-called intra-cloud lightning that occurs between clouds. Thanks to the amazing efforts by the NASA's Fermi Gamma Ray Burst Monitor and the team led by Dr. Michael Briggs, we now have in our possession a really unique data set. For the first time ever, we have 900 plus TGFs that have been collocated with what I mentioned before, the IC, the intra-cloud lightning. From these 900 something TGFs that have been collocated with ICs, we're lucky to have 24 over areas where we had the NEXRAD ground-based radars as well as atmospheric soundings. So the question that we asked is, what type of storms create these TGFs that we see? The results have showed us that a garden variety of storms from really strong, and I will show you examples in the next couple of slides, from the really strong storms to marginal convection, in other words, to like a day that we have today that maybe has produced a couple of lightning strikes. We did see a TGF, and here are some examples. What you see here is what we call the reflectivity echoes from the radar. Red means lots of precipitation, all the way to purple, which is like the lowest reflectivity that the radar can pick up. That is an example of a strong storm which would produce lots of lightning as well as lots of precipitation, as well as hail or graupel. Conversely, this is a weak storm where you can see for yourselves that we barely have red and yellow colors, which we're left with the green and the blue. Lower reflectivities. It's a very, very weak storm, which we expected to have only a few convective activity, like few lightning strikes. The common denominator between the TGFs, despite the fact that they come from disparate types of storms, is that they all originate from the highest or among the highest parts of the storm. The implication here is that the higher the TGF is occurring, the less the air and the water vapor that is above it. Therefore, the attenuation is much less, and that facilitates the TGF to reach the sensor, in this case, Fermi. Conversely, if the TGF is lower, which there is no reason for us to believe that TGFs are not produced at lower altitudes, nevertheless, the water vapor and water content and so forth above the TGF is much larger, therefore the attenuation is also larger and it cannot reach the sensor. So what the future holds, it's definitely not a case closed in terms of TGFs. Currently, the UAH, we're studying TGFs all over the other parts of the world, like Australia, Indonesia, and so forth. We're in the process of acquiring radar data from these countries. It's not as easy as it may sound. We're also looking at the storm phase, which may play a role in the TGF production. In the near future, that will be like almost a year from now, we're going to have the GOES-R launch, which will be having on board for the first time ever, from the geostationary lightning mapper. In other words, we will be able to observe total lightning activity from a geostationary orbit, which eventually will allow a much, much larger sample of collocated TGFs and lightning. Before I finish, I would like to acknowledge, of course, NASA, UAH, and GOES-R, GLM funding and research support, the entire NASA Fermi GBM team, NOAA for the NEXRAD data, and the University of Wyoming for the sounding data. Big thanks to the wizards at the Goddard Scientific Visualization Studio, which produced an amazing animation, which I will show you. It only takes 2 minutes. Last but not least, sincere thanks to the AGU committee for this opportunity. Thank you for your attention, and let me bring up the animation. Nope. Just give me 1 sec.
Deep within their roiling clouds, thunderstorms hold an elusive surprise. Under just the right conditions, they produce some of the highest energy radiation naturally found on Earth, terrestrial gamma ray flashes. or TGFs for short. Studies by NASA's Fermi Gamma Ray Space Telescope have shown that TGFs fire up about 1,100 times a day. Now, new research combines Fermi detections with ground-based radar and lightning location data. These studies show that TGFs come from more diverse types of storms than previously thought. In a thunderstorm, collisions among rain and snow cause different parts of the cloud to develop positive and negative electrical charges. When the strength of the electric field overcomes the insulating properties of air in the thundercloud, a lightning flash occurs. Most lightning occurs entirely within the cloud and is called an intra-cloud flash. All lightning produces a strong and sudden change in the storm's electric field, but the upward portion of an intra-cloud flash sometimes sends a surge of electrons rushing toward the upper part of the storm. Reaching speeds nearly as fast as light, these accelerated electrons give off gamma rays when their paths are deflected by air molecules. Using global lightning location networks, scientists can determine a TGF position more accurately than with Fermi data alone. 24 localized TGFs occurred within areas covered by next-generation weather radar systems. This gives scientists the opportunity to begin studying the kinds of storms that produce TGFs. These slices of radar data capture different types of storms encompassing a wide range of updraft strengths. Even the weakest of them produced a TGF. Another finding, TGFs seem to occur in the same altitude range, between 7 and 9 miles high. Lightning can form at much lower altitudes, so there's every reason to think TGFs can too. But gamma rays from TGFs occurring deeper in the atmosphere are greatly weakened. They're too dim for Fermi to detect, which probably means the satellite is undercounting them. TGFs may be far more common than we think. With this knowledge, scientists can design experiments to track storms and study how TGFs relate to their strength in evolution. This will give us an even better understanding of planet Earth's most powerful natural particle accelerator.
Are we all done? Thank you very much, speakers, for your talks. And we open up the floor now to questions. I just want to say before we take any questions, we welcome questions from members of the press. And if you're not a member of the press, we ask that you please do not ask questions. Thank you. Also, if you're a member of the press asking a question, please identify your name and your affiliation when you ask your question. So, are we ready? Anybody have a question?
Hi, I'm Mark Fischetti from Scientific American. Given the energies and all that, it's, as you said, surprising. How come we haven't been aware of these before?
Let me take that one? Okay. Well, they were discovered in 1994 by the BATSI instrument on the Compton Gamma Ray Observatory. And for quite a while, we weren't sure what to make of them. We originally guessed that they were coming from sprites at high altitude, and realized after a while that that was wrong, and finally figured out they were coming from thunderstorms. So they'd been seen for a while, but they're very difficult to study. I mean, as Pavlo was saying, it's very challenging to do measurements inside the thunderstorm, to be in the right place at the right time. You really need spacecraft overhead to do this, and there aren't that many spacecraft dedicated to measuring TGFs.
Do we have any other questions?
Hi, Liz Gallagher from Environmental Research Web. Please, could you comment on how TGFs are helping us to understand storms, what they've helped us find out, and what we still need to know?
You want me to do that one? You go ahead.
Yeah. Well, it has been a surprise to us, to the science community, that TGFs can pretty much originate from any type of storms. Now, as you very well said, what can TGF tell us about the storms? That is, thank you. That is currently an open question. I don't know if Professor Dwyer has a different opinion. We were discussing that like half an hour ago, and I believe you.
Okay, let me give you an example. We don't really understand how lightning gets started inside thunderstorms. That's called the lightning initiation mystery. lightning strikes the planet Earth probably, 4 million times a day, and yet we don't understand how it gets started inside thunderstorms. What we do know is when the thunderstorms emit these gamma rays in the form of a TGF, that's happening right there in the mix around the time lightning's initiated. We know that the TGFs are produced by strong electric fields, which also may be initiating lightning. So we can think of these gamma rays as a probe for looking down deep inside the thunderstorms. These are measurements that are difficult or dangerous to do otherwise.
And I have a question from the chat from Irene Klotz from Discovery Channel News Reuters, for whomever would like to answer a two-part question. Have you seen differences in X-ray and gamma ray emissions from different types of lightning, and what seems to be the difference between whether weak or strong TGFs occur?
Okay, so we've seen there are different types of lightning. There are different processes within lightning. Most of the X-ray emission seems to be coming from the leader phase. That's when sort of the spark is moving through the air. And we know that there are different kinds of leaders that propagate. There's step leaders, there's dart leaders. They all seem to emit similar kinds of X-rays. These are hard X-rays in sort of in the, like I said before, in the CT scan kind of energy range. What was the second part of the question?
What seems to be the difference between whether weak or strong TGFs occur?
I don't know if we know the answer to that. I don't know if anyone else has.
No, but yes, Professor Dwyer is right. We don't have a.
Can you talk into the
answer.
microphone, please?
We do not have a definite answer on the question that you just asked. It's also an open question. You say it's a pretty recent finding, and we may be able to send to Mars with millimeter precision robots, but nevertheless, TGF or lightning for that matter, still hold many secrets. So
it's really challenging to make progress in this field because the measurements we have are made by spacecraft. So you're really only going to detect the ones that are really high up near the tops of these tall storms. And there's so much atmosphere between the spacecraft and the thunderstorms. You need a tall thunderstorm to have a chance to see these things, even though they're really bright at the thunderstorm. So we really need to get in close with aircraft, but again, that's really dangerous to do.
Okay, thank you.
Hi, Kiki Sanford from This Week in Science and Boing Boing. I'm wondering what the threats are of these energetic particles to aircraft. Obviously, in the experiment, it was fine for the aircraft, but when we're looking at lots of commercial flights traveling potentially through storms, are you seeing any dangers to the public?
You want me to do that? Or you want to do that one?
Yeah, let
Go
me
ahead.
answer it. It has been investigated by Professor Dwyer and published recently, but as you know, usually pilots are avoiding thunderclouds and do not fly inside due to turbulence, due to icing, and some other severe events. But you can just add the hard radiation to this list. But what we see is that lightning is very bright, and it may pose some serious dose, although it still needs to be investigated further. We want to know more about their spatial distribution, for instance, of this X-ray burst in order to calculate it correctly. Yeah. And, well, yeah, this is my answer.
Hi, Tim Olson from Earth Magazine. You mentioned that these are some of the highest energy events that happen on Earth, and I was just wondering if you could talk about a little bit about the range of energies that are given off by these, and then also if you can kind of put it into comparison, some other comparison that we can visualize perhaps.
Okay, you guys want me to do that one? Okay, so the energy range of TGFs. They go into the many tens of MeV. I'll put that in context in a second, up to maybe easily 40 or 50 MeV. There's been some measurements by the Agile spacecraft up to 100 MeV. These are incredibly high energies. I mean, to give you a sort of an energy scale, so 100 keV, 100,000 electron volts, would be the energy scale that you would measure medical X-rays in. And so we're talking hundreds of times more energetic than that, the energy of the X-rays, the photons than that. So these are the kind of energies that you might expect to see if you, you had a particle accelerator, yet these are being made inside thunderstorms, under the pressure of the atmosphere. Normally, you expect to see radiation produced like this in vacuum. So you see lots of gamma rays being made in outer space by exploding stars and black holes and things. So it's really a surprise to get such high energy radiation from a thunderstorm. In terms of the brightness, we know that at the source there's about 10 to the 17, so one with 17 zeros behind it, high energy electrons being produced over a period of tens of microseconds to hundreds of microseconds. So it's a very short, bright burst of very high energy electrons that then make the gamma rays.
It's good, good question. I had the same one, and now so the follow-up is to the earlier question about threat to planes. Are we worried about the planes or the pilots or the people in them? And when you start to talk about those energies, are people in planes going to start to worry if they see thunderstorm outside their window?
Okay, well, let me go ahead and take that one too. So first of all, people don't need to worry about TGS when they get on an airplane. I've studied these a long time. I feel perfectly comfortable getting on a plane with my kids. So it's safe to fly. Don't let TGS stop you from flying. It's a concern if you're a research pilot and intentionally flying into thunderstorms, because you need to be inside at exactly the wrong place at exactly the wrong time and hit directly by one of these. Being near is not a problem. You have to be hit directly. If the aircraft is hit directly by the electron beam that makes a TGF, these electrons are so high energy they can penetrate the aircraft, go right through the aluminum skin, right through the seats, right through everything, and into the passengers or individuals inside the aircraft. Somebody that struck, this is still research in progress, but the results so far show that if an aircraft were in the wrong place at the wrong time, you would get sort of a whole body CT scan worth of radiation in a few tens of microseconds, very short time period. This is something that's not necessarily great, but it's not going to kill you. In terms of the aircraft itself, people have done some work on this. There's some research going on what happens to the electronics, but there's nothing definitive on that. Probably the aircraft would do fine.
More questions? Any from the chat? Okay, then that wraps up this press conference. Thank you, speakers, and everyone for participating. Our next press conference will take place at 11:30, and it will be about smog and soot in the Middle East.